Hello, everybody. My name is Andrei, and today we're going to talk about data visualization at scale, or how to display a gazillion of metrics and keep your sanity. But before we get started, let me say a few words about myself and my current company. So, I like calling myself a full stack TypeScript and JavaScript developer, and that means a fair share of React on the front end, some Angular, and some other overhyped thing. And on the back end, it's mostly Node.js, but I also had some production experience with Python and some academic experience with C and C++. I used to work for two major outsourcing companies in Russia, and now I'm super happy to be part of the family at Hazelcast, where I do everything related to JavaScript. And last but not least, I truly love open source with all my heart. And for you to understand the problem that we faced, you have to know what we do at Hazelcast. At Hazelcast, we build enterprise-level in-memory data grid. It sounds fancy, but basically it's just an enterprise cache, distributed enterprise cache that can fit a lot of data. And I'm working in management center team, where we basically building the admin panel for our distributed cluster. And for every member in that cluster, we collect lots of data. And when I say lots of data, I truly mean lots of data. For every member, we collect around 700 metrics. And we need to somehow visualize those metrics. If we had only one Hazelcast machine, then probably we could have allowed our users to pick the metrics they want to see directly via some sort of drop-down list of checkboxes, whatever, and display the metrics that they chose. However, it gets kind of more complex when you have not a single machine, and it gets even more complex when you have really lots of data sources. I think the largest known Hazelcast cluster is around 120 machines. So 120 sources of metric data. If we choose only one metric out of 700 and display this one metric for all 100 nodes in our cluster, probably the graph would be slightly unreadable. So what do we do here? I think that the only choice that we have is that we have to somehow display less, and therefore we have to filter. At this point, you might be asking, why do you even care? It looks like some sort of distributed systems problem, and maybe you won't even face it in 99% of cases. I beg to differ. In fact, this problem is a pretty universal one. Say you develop a payment processing system, and your metric is cash flow, and you have like 200 countries. And you want to find some countries that have extremely low cash flow, extremely high cash flow. Or, for example, you started an ad campaign and you advertise, well, whatever product that you have. And you placed it on Google Ads, on Facebook, and you split your users in several groups, like some users who love cats, some users love dogs, some users love playing computer games. So you have like multiple sources of data, and a single metric that you're looking for is how many of those users inside of that group clicked on your ad campaign. There you would have the same very problem. You would have multiple sources of data, like multiple user groups, and a single metric. So as we can see, this problem is pretty universal. And before we go any further on how to find the abnormalities, we first need to answer ourselves, who are our users? And at Hazelcast, we have established that we can split them into major groups. There will be cluster admins. They read our manual from the first page to the last page. They know everything about Hazelcast and how it operates. And we have developers. They want to start it fast and see the abnormalities right away without having that deep expertise at Hazelcast. And once we establish these user groups, we need to answer, what do our users want? And in our case, we have admins who want to find some sort of abnormalities in our clusters. So if we have like 30 machines, our admins want to see that one machine who has some sort of abnormal behavior. Later on, we will use the term time series multiple times. So let's define what a time series is. Let's settle that a time series is a list of objects, and each object has some sort of timestamp and a value. And since we have already decided that we have multiple sources of data, it means that we're going to have multiple time series. And now let's get visual. Take a look at these three time series, purple, red, and green. How do you find an abnormality in these time series? First, we need to find a constant associated with each time series, because comparing time series directly is, well, I wouldn't say impossible, but it's definitely super complex. But if we calculate some sort of scalar out of each time series, then we can compare scalars, and that is, if not trivial, definitely much simpler. So what we're looking at is three constants, three scalars. Now we need to somehow identify the abnormal scalars. And to do that, we might declare some sort of a range and say that all constants, all scalars that fall into that range, they are considered normal. And all constants that fall out of that range, they are abnormal ones. So we have kind of broken down our problem into two smaller, simpler problems. Problem 1, calculate scalars. And problem 2, find normal range. Let's start with problem number 2 because it's kind of simpler to tackle. And first, we can have some static ranges. Say you have 30 machines in your cluster. Each machine has 16 gigabytes of RAM, and then knowing that and having those kinds of guarantees, you can say right away that probably you shouldn't exceed the memory limits. Moreover, if you know Hazelcast well, you probably can establish that the normal range for your RAM is going to be from 10% to 90%, from 1.6 gigabytes of RAM to 14.4 gigabytes of RAM. However, we cannot use static ranges at any time for any metric, because some metrics, they do not have this well-known, predefined upper and lower limits. If we go back to that example where we developed the payment processing system, the cash flow is going to vary day by day, week by week, season by season. Probably is going to be some sort of Christmas sale, and it's going to affect the cash flow significantly. So I think you get the point, right? So we cannot always have some well-known upper and low boundaries. And that means that we have to calculate the range dynamically, or we have to somehow compare peers, and based on the data from peers, calculate this dynamic range. To wrap this up, we can say that static ranges, they're simple, they require less CPU and memory, they can potentially be applied to unlimited list of scalars because you can apply, well, you can see if a scalar fits into a range one by one, but they have some restricted area of application and they require deep knowledge of the system. And dynamic ranges, they can be applied to any metric in the cluster. They do not require any deep knowledge of the system, so they can be used at any level of expertise. However, they are more complex. They require more CPU and memory because you need to somehow compare the time series, the members, and etc. And they can be applied to a limited list of scalars because, well, you have to aggregate the data and you have to keep all the time series in memory at once. Now, let's take a look at some concrete examples of how we approached these two problems at Hazelcast. We have defined 6 filters: peak top 3, peak bottom 3, average, top 3, bottom 3, outliers, and manual selection. Let's start with the most boring one, manual selection. Basically, we allowed our users to pick the members that they are interested in and pick the metrics that they want to see. The only restriction that we have is that we do not allow our users to select more than 12 graphs. Going further to pick top 3 and pick bottom 3. Take a look at these 3 time series. For the peak filters, we take either the peak maximum value or peak minimum value, and for this case, let's use the maximum value as our constant. So each one of the time series is associated with its maximum value, and then we use this maximum value to find the top 3 or bottom 3 time series. So the algorithm looks like this. For the peak top 3 filter, we use mathmax to find the maximum value for each time series. Then we sort the time series in ascending order based on the found value and take top 3. For the peak bottom 3, we use mathmin, we do the same sorting, and we take bottom 3. And at this point, you might be asking that the graph that we had before, it looks kind of weird, right? Why, just why a graph that has a single value that's above the rest of the graphs and all other values below them is considered the topmost graph, right? It kind of makes sense for some metrics and for extremely experienced users who know what they're looking for. But it definitely doesn't make too much sense in a more general case. Here starts a tale of mean and median. Say you have 3 jacks and 1 bob. Each jack has $1 and bob has $100. On average, by arithmetic mean, each one of them has around $25. But on median, each one of them has a single dollar. And speaking the language of math, for the mean, we take the sum of all the values and divide it by the number of those values, and for the median, we sort the list of values and take the middle element. Or if the number of elements is even, we take the average of 2 middle elements. However, even with this approach, even if we take the median or mean, whatever, we still have a problem. Take a look at these 2 graphs. They both are going to have the same mean, they both are going to have the same median, but even intuitively, does it look like they should have the same average value? I don't think so. The problem with how we calculated the average before was that we took only the value for every point. We didn't take into account time. And if we took into account time, it kind of means that we have to calculate the area under each curve. And that area is going to reflect both value and time. That area is going to be the true reflection of the average value for every time series. So, ladies and gentlemen, behold His Majesty definite integral. And there are multiple ways to calculate the definite integral, but we're going to cover only the most popular ones. And the most simple way to do it is by midpoint rule. In essence, we have to imagine that we have rectangles formed by every point. We have to calculate the area for every rectangle, and we have to sum the areas of those rectangles. The next one, a fancier one, is trapezoidal rule. And this time we calculate the areas of trapezoids, not rectangles. It's a little bit more accurate. And the last one that we're going to consider is Simpson's rule. It's as fancy as we are going to get today. And for Simpson's rule, we're going to take triplets of data points, and we'll try to draw a curve that is going through all three dots. But I have kind of cheated. I have added an extra dot. Why? The problem is that in order to find a curve, we need to solve a second-degree equation. And that second-degree equation has three unknown variables, a, b, and c. For every dot, we know x and y. And to solve an equation with three unknown variables, we need three equations, therefore three dots. So what do we do with the last two dots if it turns out that we have two dots in the end, not three? First, we could use the trapezoid rule to calculate the area of the last segment. And second, we could do something more interesting. We could remember that we have third-degree equations. And to solve a third-degree equation, we need four dots. So the idea is to use Simpson's rule and keep solving second-degree equations up until the point where you have only four dots left. And for the final four dots, solve the third-degree equation. However, I tricked you once again. I moved the dot. Why? Because if I didn't, then the curve would go beyond the screen and you wouldn't see the complete curve. And I think it kind of demonstrates that Simpson's rule might be the most accurate rule if you know the shape of data that you need to apply it to, but at the same time, it might be vastly inaccurate. And for it to be accurate, ideally you would need the original function, not a copycat, discrete copycat that we have here, and ideally you would need to sample it yourself, or at least you would need some third-party system to provide you with guarantees that these samples of this function are evenly distributed. So it's complex, unreliable, and etc., etc. And it leaves us with only two rules for our use case, midpoint rule and trapezoidal rule. Let's take a look at the code. So in order to calculate the average by midpoint rule, we have to keep track of total area, and for every 2 points, we have to increment this total area by the first point's value multiplied by the time difference between the 2 points. And then, in order to find the average by the definite integral, we need to divide this total area by the total time that we have. And for average by trapezoidal rule, we do pretty much the same, but the increment now is the average value of the 2 points that we have in our for loop. If you're in doubt why the increment now is an average value of these 2 points, let's go back in time to our high school years and remember that the area of the trapezoid is the area of the rectangle that we had before and the area of the triangle that we added. And the area of this new triangle is going to be equal to the half of the area of the rectangle on top. So therefore, the average value of the 2 points. And if you run some benchmarks, you can see that both of these rules are pretty performant, and even for 10,000 elements, the average by trapezoidal rule function gives us around 15,000 operations per second, which is just good enough for our use case. And we decided that we're going to proceed with trapezoidal rule at Hazelcast, since it's kind of the best performance to accuracy ratio on the market. With all that knowledge, let's jump to the next filters, average top 3 and average bottom 3. Now, instead of taking the absolute max value, absolute mean value, we use the trapezoidal rule to calculate the average for every time series. And the algorithm looks like this. Calculate the average using trapezoidal rule, sort the time series, and take top 3 or bottom 3. And now our jewel in the crown, outliers. Before we do the math and proceed to the algorithm, let's remember that we have multiple sources of data. Say we have 100 sources of data, and we have identified 20 of them as abnormal ones. How do we display them? We could potentially draw the lines for all the members and highlight the lines for abnormal members in red. But that would still be the same problem as we had before. The graph is unreadable. What if we display only the abnormal values? If we do that, what's our baseline then? What's the normal value? So we kept thinking what we could do, and we decided that we need to display the abnormal values. And for the normal values, we need to calculate some sort of aggregate baseline value. And we need to display the abnormal values and that baseline value. However, we have identified 20 values as abnormal ones. And if we display 20 graphs for the abnormal machines and 1 graph for the baseline, it would be 21 graphs, and I'm still doubtful that 21 lines on a single chart is definition of readable. So what can we do here? We can display only some part of those values that we found abnormal. In our case, we sort these values in ascending order by their deviation from the baseline, and we display only top 3 abnormal values that have the biggest deviation from the baseline. Let's take a look at the next time series. The green time series is going to be our baseline. The black ones are going to be our normal time series. And the red one is going to be our abnormal time series. And the algorithm looks like this. We request our cluster time series from the backend, and we also request some sort of median time series, artificial time series that backend calculates on the fly. We use that median time series as our baseline. We feed those time series to average by trapezoidal rule to get the scalars. Then we use the scalar for the median time series as our baseline, and we find the difference between the cluster time series and median time series. We sort the cluster time series in ascending order by their deviation from the median time series, and we display the outliers and the median. And in real world, it looks like this. Our dotted line is our baseline, and our solid line is our outlier. And in this graph, we have two metrics. We have used heap and used native, and you can see that for each one of them, we have a baseline, and we have a single outlier that we found in our system. Thank you for being here today and exploring together with me data visualization at scale and how exactly we did it at Hazelcast. Here's a link to a related article and a link to the list of my talks. And if any point in time you would like to chat about data visualization, JavaScript, TypeScript, web development, or boxing, feel free to drop me a message on Twitter or on email, and the QR code contains a link to these slides. Thank you.